So let me start. So first we said that there are at least two ways, two definitions, if you want, of a conformal field theory. What is a conformal field theory? Is a theory without scale. But more than a theory without scale, is a theory which has this local scale invariance. It's a theory where you can rescale, but you can rescale by different amounts in different regions of space-time. Perhaps it's not so surprising that if a theory is scale invariant, it's scale invariant at a more local sense, or perhaps it is. So this is, if you want, one definition that tells you that a CFT is a theory where correlation functions in two spacetimes that differ by a local rescaling, so-called a Weyl transformation, transform in a precise way. And now another definition of a CFT that is also sometimes convenient to think about is that a CFT is a table of numbers, a table of dimensions and structure constants, but not any table of numbers because they form an algebra, they form an OPE algebra that tell you that you can compute correlation functions by considering the operator product expansion in different order. And this CFT data must obey the so-called bootstrap equations, which are graphically represented here. Where I want to emphasize, you agree that these equations are very precise things. By this, we mean sum with structure constant, conformal block in the middle, and so on. Is it clear?
May I ask a question?
Of course.
If you consider, for example, 5-point function, can you get new constraints?
No, it's not obvious, but you get no new constraints from starting with 5-point function. Because in a way, what are you doing here? You are imposing that your algebra is associative. You are imposing that you have your 4 points, and you can do either these two or these two. Now that your algebra is associative, putting more points and doing different orders, why would it work if the algebra is associative? So if you already imposed associativity, there will not be anything new for 5 points. Okay? In particular, just to make it maximally explicit, we saw that a correlation function of 4 points, 2 and 3 points were totally fixed by symmetry, unless you start considering many operators with spin. But if you have just one operator with spin, or a 2-point functions of 2 operators with spin, unless you go wild, you can fix 2 and 3-point functions by symmetry. And then 4-point functions, you can strip out some part that transforms nicely under rescaling and so on. And then you have a function of cross ratios, u and v, or equivalent z and z bar, where u and v, or equivalent z and z bar, are just conformal cross ratios that are quantities that are invariant under rescaling, rotation, inversion. So they are invariant under all conformal transformation. And as such, you can a priori say nothing about this function f. It's not constrained by conformal symmetry. So it is constrained, on the other hand, by imposing that these bootstrap equations, but typically those are too hard to tame, so we are not going to go there until the last lecture.
To say that algebra is associative, we need to write only 3 basically elements. Okay?
That's right.
So it's confusing why we constraint on function.
Because just with 3 elements, things are too simple and they are just fixed by symmetry. So it's like you have this relation that must hold inside any correlation function. And you put extra probes. It is true that in principle you could take a 3-point function and construct it by taking the OPE of any pair of operators. And that is true. That holds. And we imposed that we fixed the coefficients of the descendants compared to the primers in such that it would work. So that we already did. So perhaps you are right that my first answer was a bit too fast, because indeed, for associativity, normally you would imagine just 3 points, and here we know that in fact from 4 points we get some new constraints from these relations. It's true, yeah. So it's perhaps not so trivial to show that for 5 points you get nothing new. But it's a non-statement. I know it is true. But perhaps it's an interesting exercise to show it. You can try to give it a look. Okay? It doesn't mean that are all the constraints in conformal field theories. You could imagine doing something fancy, like imagine you take an operator, or you take 2 operators, they fuse into another operator, and this operator goes around the world. And then they annihilates back and forms some kind of loop. How could you imagine getting some kind of constructions like this? If you start putting your quantum field theory in non-trivial topologies. So then you could ask, if I now start putting my theories in non-trivial topologies, and we'll get different pictures where I start having this kind of networks, but now where some of these legs wrap some cycle of my spacetime and so on, will I get new constraints? And that, I think the answer is yes. It's very likely that there are yet new constraints to be understood in conformal field theories, most of which were not explored yet in detail. So that, I do think that there is no reason to believe that we did explore everything there is to explore there. Anyway, today I'm not going to discuss that. Today we are going to explore this connection between a 4-point function and its decomposition in terms of conformal blocks. As we said, a conformal block is very much the analog of a spherical harmonic or of a plane wave. If you want to sum over stuff that has fixed momenta, use plane waves. If you want to sum over things that have fixed angular momenta, use spherical harmonics. Similarly, if you want to sum over representatives that have fixed dimension in an angular momenta, that is, things that transform, that are in some representation of the conformal group, you use the conformal blocks. Is it clear? Okay. So let's, and then these conformal blocks, we said that we could fix them explicitly, remember, because we know a 3-point function. We could put the OPE inside the 4-point function. We know the OPE coefficients. We know the 3-point function. So a priori, this is a known function. And it was given by this function where this h was just some simple hypergeometric function. Okay? So how could we try to understand this in some more detail? How could we rederive this result? Now that we know what it is, it's often easier to rederive things once you already know what they are. So how could we go about trying to understand what this object should be and explain a little bit where these hypergeometric functions are coming from? And the basic idea is the following. If you want to study what flows from some region, like these 2 points, to the outside of these 2 points, what you can do to measure what is flowing is you can act with some generator that measures the state flowing here and tells you its quantum numbers. Okay? So if you have some state that flows from here to here with some energy and some angular momentum, you want to act with some operator that will measure the energy and angular momentum of that state. Okay? Now, what could be a good operator to act on? Well, you could imagine acting with a Casimir of the conformal group. And why would this be a clever idea? Because the Casimir of the conformal group is a Casimir. So what does it mean it's a Casimir? It means that it commutes with all the generators of the conformal group, right? So this Casimir of the conformal group that was written yesterday in the blackboard, how was it? It was something 1/2 mu nu minus d square this object that commutes with any generator of the conformal group is kind of an ideal thing to act to see what flows from one group to the other. Because what does it mean? Why are Casimirs useful? Because a Casimir gives the same thing on any element inside the same representation, right? That's how you find, for example, the equation that determines spherical harmonics. You say J square acting on spherical harmonic is proportional to the spherical harmonic. And by imposing that the Casimir acting on some state, gives some number times the state, you will get the same thing whether you have the state or some state that you obtain by some simple rotation that moves you inside the same representation, or some state that you get by acting with P, which means that you consider a descendant. So a primary and all its descendants have exactly the same Casimir. It's like saying that you are in some spin 1 representation. Thus, SZ equal 1, 0, or minus 1, they are all in the same representation. And if you act with a Casimir of SU2, you get the same thing in any element that just tells you in which representation you are. Okay? So this is kind of philosophical motivation. Let's do it in practice. Let's see what we should do. So what we do is the following. We have our points here. Let's say this is point 3, 4, 1, 2. And we connect with the Casimir on group 1, 2. So we can construct the Casimir 1/2 J1 plus J2 square. So we construct the Casimir related to these 2 points. Okay? Is it clear? Where these generators, they act on this point 1 and this point 2. Okay? This is equivalent Do you agree? With acting with the generator on points 3 and 4. With a Casimir on points 3 and 4. Why? Because if you act with a full generator on a correlation function, it is 0, because that's the statement of symmetry. If you rotate everyone, it is 0. So I can, when acting with my Casimir on the correlation function, I can either act with J1 plus J2 or with minus J3 minus J4 square, which is the same as J3 plus J4. Okay, it's just a statement of conformal symmetry. If I rotate everyone, I'm doing nothing. I should either act here or act here, and it is the same thing. Okay? So this is because for any generator, if you have J1 plus Jn, it kills the endpoint function. Okay? Well, you probably have to take out this part that transforms covariantly, but once you take out a trivial part, this should be invariant, so it's killed by any generator. If you make a dilatation, this object is invariant, and so are the conformal blocks, and so on. Is it clear? And now let's go on and try to act with this Casimir on our conformal block. So let me remind you what was our conformal block. Our conformal block, for a given primary of dimension delta and L, this object there was given by summing over the primary and all its descendants, right? B mu1 up to mu n of x2 minus x1, derivative with respect to x1 mu1, derivative with respect to x1 mu n. And this was acting on a correlation function of operator with some dimension and some spin at some position x2, say, and then the operator 3 at position x3, and the operator 4 at position x4. Okay? And what I wrote it here with some space, because if you act with the Casimir that will depend on J3 and J4, you can see that you can take the Casimir, nothing here depends on 3 and 4, and you can insert here the Casimir. So here is where you would put 1/2 of J3 plus J4 square. Right? So if you would act with this Casimir on this conformal block, this Casimir that acts on points 3 and 4 goes through, and now is acting here. But now that it is acting here, because J3 plus J4 plus J new guy is equal to 0. So now that I am here, I have the freedom to replace this by 1/2 of J of this new operator square. Right? I have this freedom. Do you agree? And then the Casimir acting on some operator with some given dimension and some spin just gives a number that depends on the representation, which is something like delta minus d plus L minus d plus 2, something like this, right? Times the state in the same representation. It's a Casimir, so whenever you have some state in a given representation and you act with a Casimir, you just measure its representation, and what you get is the value of the quadratic Casimir times the state itself for any state in that representation. So we are done. Now we are done. What did we arrive at? We start with some differential operator that is a differential operator in x3 and x4, right? It's an operator that you can write as a differential operator, right? So you know what how this acts as a differential operator, this, and this. So you start with a differential operator, which is a quadratic differential operator. Why quadratic? Because there are two derivatives, you see. So you start with a quadratic differential operator that acts on the points x3 and x4. Do you agree? And you act with this quadratic differential operator on the conformal block. What am I telling you that it should give? By what I just explained, it should give back the conformal block times a number. So now, when the dust settles, this is what you get. You let the differential operator pass by this space-time dependence that is trivial, And you end up with an effective quadratic differential operator that acts on the juicy part of the conformal block that only depends on z and z bar, doesn't care of only this function of the conformal block. And this should be equal, okay, there is a 1/2 from the j square convention, delta, let's go to 4 dimensions because this is the solution that is written there. Times the conformal block. Where this quadratic operator that you can read off from just computing the Casimir and seeing how it acts on these cross ratios, you just write it down and see what it takes the following form. Z square, 1 minus z, d2 dz square, plus the same thing with z and z bar exchanged, plus a term 2 z bar over z minus z bar. This is kind of the even part, and now it's the odd part, times 1 minus z d dz minus z replaced by z bar. And we have a differential equation plus boundary conditions that come from the fact that we know very well how this object behaves in the operator product expansion limit when z and z bar are very small. Because this is, after all, how we fixed this function as an expansion at small x yesterday. Do you agree? Yes? No? Maybe?
Can you repeat by the scale standpoint function?
Why what?
By j1 to j plus scale standpoint function?
Because acting with a full generator on a correlation function, what does it mean? Take, for any generator, I can put an index A here that tells you take any of the generators of the conformal group. So take, say, rotation. What are you saying? You act with the rotation means you rotate all the points. So if you rotate all the points, everything is invariant. Nothing changes. This is the definition of a symmetry, right? This is the definition of symmetry. It's just saying that if you have a symmetry and you act with your symmetry, you get 0. Quantities that are symmetric means that they are killed by the generator of your symmetry.
But it could be covariant.
No, it could be covariant. This is what I said. I'm always oversimplifying a little bit and saying it is 0 after going through this. For example, rotations, it's really 0. Because if you rotate, this is invariant and this part is rotation. Dilatation, it's a bit covariant, indeed. Okay, this part picks some trivial scaling. But this I'm not even discussing. I'm already thinking about the generators after going through this trivial factor. Right? I mean, yeah, covariance or invariance is something that, okay, people make a big fuss out of it, but it is just that you properly take out some part that you know is covariant, and then the juicy part is the invariance part. I mean, covariance or invariance just means that either it is killed or you know what it gives. So, I mean, in practice, it's the same thing. I mean, it is just that you can use this symmetry. Okay? Mm-hmm. No.
Why is j in the conformal group? Conformal algebra? Because I know how j squared is.
No, j square, this is definition. This object j square is called the Casimir. I write it as j square to remind that it is the same as j square in angular momentum. But if you want, call it something else. You can call it C of Casimir and put a hat on top. And it's a sum of generators. This is when I say JA, this A index is one of the generators of the conformal group. It can be M, D, K, or P, depending on what A is. Whatever it is, if I act with a rotation or dilatation or special conformal on the full object, it is invariant or covariant if you want. So what is interesting is not to act with the full thing. The full thing is what we know. Is to act with partial thing. When you act with a partial thing on a system which has 2 points and 2 points, by acting with a Casimir on one group, you are measuring what is flowing from that group to this group. And this is a general lesson in physics. If you want to study what flows from group A to group B, you act with the symmetries of your system on group A. And is it more clear? Any question? You got a question? Sorry? Science? Oh, science I'm doing randomly, more or less. I mean, there's no correlation between what I write and the correct science, of course. I thought that was self-evident, yeah. Okay, So this is the differential equation. By the way, if you want to keep track of d, this 2 is d minus 2. And it shows that in 2 dimensions, this term is 0, and the differential equation is simpler. It is just function of z plus function of z bar, which is maybe what you should expect, because in 2 dimensions, you know that the conformal group factorizes into holomorphic and anti-holomorphic. And it is very common that it should indeed become something of z plus something of z bar, and this is exactly what happens. And in 4 dimensions, it is not the case. It doesn't factorize into function of z and function of z bar because of this extra term. But the failure to factorize, if you see, is still very minor. It almost wants to factorize. It is just that there is some function z bar over z minus z bar. But if it was not for this factor, it is indeed almost factorized into z and z bar. But this is what it is. And now it is perhaps not surprising. Now the claim is much simpler. I'm just telling you that this differential equation is the differential equation for hypergeometric functions. So now this is something you can ask Mathematica. Solve this differential equation with this boundary condition, and it will give you the hypergeometric functions. Or even simpler, take that hypergeometric function and plug it into this equation, and you can check that it goes through. Okay? Then you have the boundary conditions that would single out which solution, but those are simple. The boundary condition that comes from the OPE just tells you that for small, if you want to be totally complete, for small zz bar, this f behaves as zz bar to the power delta over 2, z over z bar to the power L, where both these quantities are small. L over 2. Very good. So what is the geometrical interpretation of z and z bar? Z and z bar, we can think of them in the following way. We can think that by a conformal transformation, I can always put 4 points, 1 at 0, 1 at 1, and 1 at infinity. And then there is a third point that I can always put on a plane, on this plane here, at some position here. And then z is nothing but a complex variable made out of the coordinates of this point. Okay? So let me do it a little bit slower. Let's see that 4 points that we can always put at 0, 1, infinity, and the last one on a plane. So let's see if we can do it. So let's take 4 points. Now let's apply a translation until one of them is at 0. Now let's apply an inversion. Now this guy at 0, at infinity. Now we have 3 points at finite value, and one went to infinity. Now let's apply another translation such that one of them is at 0 again. The one at infinity now doesn't move because it's at infinity. Now one is at 0, one is at some random value, another is at another random value, and one is at infinity. Now let's make a rotation that doesn't touch the guy at 0, of course, that puts one of them in the x-axis, what you call x-axis. Now let's apply a dilatation that puts it at 1. And now this other one is in some other position. Now we make a rotation along this axis to put it in whatever plane we want. Okay? So we can always put it in this xy plane, and the other one's at 0, 1, infinity. And then in this xy plane, it has 2 parameters, x and y. Those are in 1-to-1 correspondence with the 2 cross ratios that we know should be the 2 parameters that are left and fixed. So these cross ratios, I can write them in terms of this coordinate z of z bar if I do this transformation. So this gives a geometrical meaning to this transformation. And it's also kind of interesting because you see that if you think from this point of view, where you have this point z, 0, and 1, you can now think that let's try to think of encircling the points 0 and z, which are the points, 2 of the points. Let's consider an OPE where we encircle these points here. And so we study what is flowing between these points and these points here. Right? So what are we doing here? We can write now this z as e to the minus tau plus I phi, some angle and some space, which are how dilatations and rotations would act, which are the symmetries that preserve 0 and infinity, how they would act on one group on group A. So this is what I said before. You take your symmetries, and you act with your symmetries on group A to find out what flows from A to B. Once you act with this dilatation and rotation on group A, this is how you parameterize. This is related to dilatations. This is the generator related to rotations. And now, when you expand the result, whatever you compute here, it will be an expansion. And you know that whatever comes multiplied by tau should be the dimensions of operators. And whatever comes multiplied by phi should be the angle of the operator being exchanged. And this is precisely what I wrote here in the boundary conditions, that z times z bar, which is e to the minus tau, is delta, and z over z bar, which is e to the I phi, is L. Times some fact, some weight here, that will depend on L. Okay? So if you were in my colloquium, this would be the analog way. This is the analog of this tau sigma and phi that I was discussing. Were you? Was someone there? Okay. What should I do? What are we going to do next? Let's see. Okay. So this is the geometrical meaning. This is the conformal block. This is all extremely general, any conformal field theory, and so on. And now I want to do 3 things in the remaining part of all these lectures. The 3 things we want to do, the outline of what we are going to do, is we are going to do first an example, which would be a prototype of the kind of computations that you find doing perturbation theory in a CFT. So we will do weakly coupled free scalars. They are in practice, they will be free. We will do just 3 level. Weakly coupled scalars and analyze the conformal bootstrap, 3-point functions, and so on. First example, we will play a bit with these scalars and see how all these ideas indeed are realized, to see that it's nothing mysterious and that everything is working perfectly. Then we will consider another example, which will be an ADS CFT appetizer, if you want. We will consider a toy model example that you can think of more as some toy model for what it would be a strongly coupled theory of scalars, where instead of weakly coupling perturbation theory, we will have some nice picture of ADS, and we will have some interactions inside ADS, some kind of cartoon like this that we will do tomorrow. And then as a third example, we will do something more complicated, which will involve the bootstrap. It will not be weakly coupled. It will not be strongly coupled. It will be the bootstrap and the 3D Ising model. And this we will do on Friday. So today it's point 1, tomorrow and after tomorrow. Okay, this is the plan for this lecture. So today I want to start with, today we are not very ambitious. We just want to understand a little bit that everything we said together works, that the 3-point functions take the form they should take, that when you decompose 4-point functions, you can read off the 3-point functions and find the results you expect, and so on. So what we want to consider is a theory with 4 complex scalars. It's a lot of complex scalars, but I just want to consider it because it gives me the freedom of considering many correlators and so on. And we are mostly going to use just 3 complex scalars, but 4 makes my life a bit easier. So consider a theory with 4 complex scalars, which are free, or weakly coupled, but we are doing leading order, so in practice we don't see the interactions. Okay? And we are going in this theory to study composite operators. We are going to study operators. For example, let's write 2 types of operators that I want to consider. One of type 1, that is just, for example, phi 1 square. Phi 1, phi 1. This is phi 1 square at some given point in space-time. And another operator that I want to consider, let's call it of type 2, would be phi 1, phi 2. Okay? This is what we want to consider. And the rules of the game is that when you have a scalar, phi1, it can only contract with its complex conjugate friend, phi1 bar, and the correlator gives 1 over x minus y squared. So we are in 4 dimensions, and we are, and everyone else is 0. Say phi1, phi2 is equal to 0, etc. Phi1 with phi1 is also 0. Perhaps that one is the one I should write. Because you have charge, so the scalars cannot, charge cannot disappear, etc. Okay? So this is the rules of the game. We want to study composite operators. Fundamental operators, they behave trivially. But because we put them together in composite operators, we will see that we can actually get some interesting dynamics, even though the underlying theory is free. They are all massless. That's why the propagator is 1 over x minus y squared. Yeah. 4 massless complex scalars. Phi1, phi2, there's phi3, and phi4. Now, these guys are primaries. They are not the derivatives of anyone, right? Phi1 squared is not the derivative of anyone. But let's now consider operators that start having derivatives. Let's find some descendants, for example. For example, the derivative, now I'm always going in this discussion to suppress indices. So when I mean derivative, I mean that it's some constant vector dotted with the derivative such that I don't need to worry in which direction it is pointing. So the derivative, for example, of operator what do I want to do here? Say operator O2, for example. What is this derivative? It is just d phi1 phi2 minus phi2 minus plus phi1 d phi2 is a descendant, of course, right? It's just the definition of descendant. So right now we are going now to study case 2 for a bit, because you see that case 2, if you want to go to case 1, just put phi1 equal to phi2. Okay? So let's stick to case 2 for a moment. This is a descendant. However, this guy, let's define O2 with L equal 1. This guy that I'm now going to write, d phi1 phi2 minus phi1 d phi2 is a primary. It is not a derivative of anyone. You can check, for example, that if you take a correlation function of this guy with another primary, with this one, say it is 0. It's obvious, right? Because you see that you have two propagators. You have this guy and the complex conjugate of this guy. And you connect it. And this object contracted with a primary gives a number, but this gives the same number, and there is a minus sign. So they are orthogonal to each other. Is it clear? It's orthogonal to the other one. So orthogonality with the other primary, it is just that you compute this two-point function. And in one case, you put the derivative in the first leg of the propagators. This is a composite operator. This is a composite operator with a derivative. And you do minus the same graph, where now you put the derivative on the second leg. But as numbers, they are the same. So this is 0. Right? So this is if I do here L equal 1, and here on the top is represented the operator with L equals 0. Is it clear? So there is one primary and one descendant with one derivative. And now you could go on. So at level 2, what do we have? So we have two derivatives now. And we have now 4 possible structures, right? You have A times two derivatives of phi1 times phi2 plus B d phi1 d phi2 plus C phi1 d square phi2. You have to show that it has the right transformation properties and that it is killed by special conformal generators. So now at level 2, we have two derivatives, right? So we have two derivatives. And there are 3 structures you can write, A, B, and C, being the relative coefficient between these structures. But again, there will be only one case that is non-trivial, because two derivatives of the operator with L equals 0 and one derivative of the operator with L equals 1, this we are not interested in. These are descendants. So there are two linear combinations of these guys that are trivial. And there is the remaining linear combination that is the interesting one that gives the primary. So these are descendants. And the primary is O2 L equals 2, which is d squared phi 1 phi 2 minus 4 d phi 1 d phi 2 plus phi 1 d squared phi 2. And you can check that this object is indeed orthogonal to everyone that we wrote before, and that it has the good correlation functions that you expect for a primary of spin 2. If you compute, say, 2-point function of this object. Is it okay? And now, we could go on and study. And you see that the pattern is that as you increase the spin, you have L minus 1 operators that are trivially descendant of the previous one, and you have one new guy. So let me write what's the general formula for the most general primary that you can have of any spin. And it's the following. So you have O of spin L. If I write here, I will not be able to lower this blackboard. So let's write the general expression for a primary. O of spin L is equal to a sum from k equals 0 up to L. So you have to I have to tell you how the derivatives are distributed, how many are on the first field, and the remaining ones are on the second field. And now I should tell you what is the weight, and the weight is binomial L k k square minus 1 to the k. Sorry? Yeah, that should be okay. Okay? And you can check that when you have L equals 2, this gives the coefficients give exactly 1, minus 4, and 1. And if they don't, this is the correct formula. I just thought that it is, and I wrote that. But I was doing it by head. So this is correct. So this is a primary of spin L. Okay? So now let's work a little bit. So this is what's called twist 2 primaries. What is twist? Twist in a conformal field theory is defined as the dimension minus L. And you see that if you take the dimension minus L, it is always equal to 2 in this particular case. Because the dimension of this object is L plus 2, 2 being the dimension of each scalar, and L being what you get by putting more and more derivatives, you increase the dimension by 1. So this is our primary, and now let's have some fun with this primary. This is a primary of type 2. And what is the primary of type 1? It is the same thing, but this phi 2 you replace by a phi 1. Can you tell me one important difference or one important, what is a bit different between 1 and 2? Other than this trivial difference, what do I have for case 2 that I don't have for case 1? You can look at the spin 1 guy. The spin 1 guy is a good example. Sorry? Well, what happens if I put phi 2 equal to phi 1 here? I get 0. So this is what you expect indeed. There is no odd spins if your object in case 1. So there are no operators of odd spin. So in this second example, this L needs to be even. Otherwise, there are no primaries of odd spin with 2 equivalent operators, which is kind of what you expect if you have a theory. Imagine you have a theory and you have 2 equal scalars, phi 1, phi 2. Suppose you put 1 at x and 1 at minus x. It's totally symmetric, right? 1 at x, 1 at minus x. Now approach, collide, and get some operator in the OP, whatever these operators can fuse with. And now it is natural that if I get something with odd spin is something that has some orientation. But where do they point? Left or right? It's totally symmetric, phi 1 and phi 1. So you could not get anything with spin 1. This would be pointing to the left or to the right. There's no way you can get any privileged direction. Whereas when you have phi 1 and phi 2, then you can, because you have phi 1 and phi 2, it's red and blue. You can have, you break the symmetry and you can have odd spins. Okay, very good. So we started. And now we are going to study correlation functions of these operators. This might look a little bit trivial, but as you will see, it will lead to some interesting observations. And I want to consider the following correlation function, for example. Let's consider a correlation function that I'm going to draw in the following way. I draw these 2 points to indicate two fields phi 1, phi 1. So this is an operator of type 1. And then I'm going to do a correlation function with other 2 operators. So this correlation function at this leading order, it is just weak contractions. I just unite all these guys by propagators. And to make sure that these are the diagrams that I need, I'm going to put here a phi 1 bar. I'm going to put here a phi 1 bar. But then here I'm going to put one of the other scalars, say phi 2, and here phi 2 bar. And this guy here, I let it be an operator with spin. And these guys here, just scalars. So then graphically, it means that this guy has some derivatives. For example, 2 derivatives that act here and 4 derivatives that act on this line. So this would be the graphical representation for a correlation function of, so this, for example, will be the example of L equals 6, 6 derivatives, and 1 operator with spin and 2 operators without spin. Okay? Is this cartoon clear? What this means? Correlation function, this operator, let's say at point x1, this operator at point x2, this operator at point x3. Is it clear what this picture means? I don't need to write down what's inside, right? So what is this? This is nothing. Let me write and it will be obvious. You sum from k equals 0 up to L, binomial Lk square minus 1 to the k. And then you have some derivatives that act here and here that are acting on these propagators, right? So I can just write n dot the derivative acting on the propagator between 1 and 2 to the power k, n dot the derivative acting on propagator between 1 and 3. I put this index to remind me on which propagator I should act to the power L minus k. And all this is acting on just the correlation function of 3 scalars, just the product of all these propagators. That is what? I have a propagator between x1 and x2. I have a propagator between x1 and x3. And I have a propagator between x2 and x3. It's a triangle as drawn here. So this is the result of this computation. I just need to perform this sum with these derivatives acting there. And now let's do this sum. It's trivial, so just take these derivatives. And you see that when you take, let me remind you, let's take derivatives of 1 over x. What do you get? Take one derivative, you get 1 over x squared. Take another derivative, you get 2 times 1 over x cubed. Take another, you get 3 times 1 over x to the 4, and so on. So you get k factorial and L minus k factorial factors from taking these derivatives. They will cancel part of this binomial here. So what I will write is, let me see if you agree, I will take out L factorial, and then the second binomial is killed by doing these derivatives, and I get sum from k equals 0 up to L minus 1 to the k, binomial L kk. Again, one of the binomials got killed by taking the derivatives, and 1 L factorial from that binomial I took out. And then you get what the result of taking the derivatives of this propagator is, which is n dotted with x12 over x12 squared to the power k. The result of taking the derivatives of the other guy, n dotted x13 over x13 squared to the power L minus k. And then the lonely propagator, that poor propagator, no one acted on him, 1 over x23 squared. This propagator that was a spectator that no one cares about him that goes between this point and this point here. Is it clear? And now what is this? Can someone tell me what this sums into? Is this familiar? Did you encounter this in your life before? When you have a sum with a binomial coefficient and then x to some power, y to... Very good. It's just a binomial development. So this is just L factorial 1 over, and actually when you take the derivatives, there is an extra factor that remains here. 1 over this factor that is there, that we just, you see, if you take 0 derivatives, you should get that factor back. So what I wrote could not be right. Right? When you take 0 derivatives, you better do nothing. So it should be there. 1 over x 2, 3 squared. And then, as you guys all said, you get just the binomial. So you get n dot x12 over x12 squared minus because there is minus 1 to the k that you can put inside one of them. N dot x13 over x13 squared, everything to the power L. So this is a very useful exercise because if you go back to your notes, this was the form that I said by conformal symmetry a 3-point function of an operator with spin and 2 scalars should have. So it's very important that we are reconstructing exactly these dependents. And all these dependents, we ought to get it. Unless if we are doing things right, we better get all these dependents. This is all fixed by conformal symmetry. And it's quite non-trivial. If you go back to your notes, you see that I told you exactly that you should get this factor here with this n and so on to the power L. And this is all coming out right. And what is not fixed by conformal symmetry is the coefficient, this L factorial here. So what is this L factorial? It's almost, but not yet, and the not yet I must emphasize, the structure constant, C12 delta L. Why not yet? Because, of course, I cannot just do a 3-point function. This will never be well defined. I could always multiply my operator by 25, and the result will multiply by 25. To make the 3-point function well defined, what should I do? I should normalize the 2-point functions first. Right? So we need to normalize the 2-point functions, of course. Up to this small issue, we computed our 3-point function. Let's normalize the 2-point function because it's also interesting. And let's normalize the 2-point function of these operators with spin. Okay. So now let's compute the correlation function of 2 such operators with spin, OL2, OL2. And by the way, here, I'm working up to 2's. There can be 2's because I contract phi 1, phi 2, left field, right field, but there is another diagram when I fill. So I'm not paying attention to 2's, but it is just up to 2's. I'll put the correct 2 at the end. But you should not trust overall factors of 2. So what do I get if I compute this correlation function? Okay, so this graphically, I have my composite operator, and I have some derivatives here, like 4 derivatives here, and 4 derivatives here, and I should distribute where I put these derivatives. You agree? So what do I do? Imagine I put here k derivatives, L minus k derivatives. I put here k prime derivatives, L minus k prime derivatives. So what do I get? In total, I'm taking L plus L, I'm taking 2 L derivatives. And whenever I take a derivative, I get a factor of n dot x, x being the separation between the 2 points. So the space-time dependency in this case comes out automatically. It's n dot x1 minus x2. It's just the total number of times I act with derivatives. So this happens to the power 2L. There are 2L of them. And then after acting with the propagators, I got 1 to the power 2 delta plus 4L. Okay, so this is the space dependence. Just write the propagators, they act with many derivatives, and you increase the dimension, and this is what you get straightforwardly just from the derivatives. And now let's write what multiplies this. What's the number that addresses this normalization? You have to sum from k equals 0 up to L. You have to sum from k prime equals 0 up to L. By the way, you could start first by doing the exercise putting different L's to check orthogonality between different operators of different spin. But I'm already assuming that orthogonality works and doing directly the normalization of the interesting one. So we sum from k equals 0 up to L, k prime up to 0 up to L. Then we have minus 1 to the k, minus 1 to the k prime, binomial L k square, binomial L k prime square. And then we take these derivatives. And by taking these derivatives, we get k plus k prime derivatives that we take on this leg factorial. And how many derivatives in the other one? 2L minus k prime factorial from taking derivatives of the second propagator. Okay? And this sum here gives 2L factorial. Don't ask me why, but it's true. I actually know how to prove it in a super complicated way of counting cats and dogs into groups and so on. But I think it would be super duper complicated to explain. It's much easier to just check in mathematics. So this is 2L factorial. So our summary is as follows. So let me write down the summary of the result. Structure constant of operators of type 1 between two trivial operators and a spin L operator is given by square root of 2 times L factorial times square root of 2L factorial. So the square roots come when you divide by the norm of the two-point function. Right? You divide, you normalize each operator by square root of its two-point function to have norm 1, and this would be the result. And correlation function of type 2 between two trivial operators and one operator of spin L, it would give L factorial. Here there's no factor of 2 because you have, I will draw what picture this will be, because now you would have phi 1, you have operator phi 1, operator phi 2, and there would be no option in the way you would contract them. Here you have phi 2 bar, let's put say phi 3 bar, phi 1 bar. So if you do this configuration, you see there is no factor of 2 from swapping this 1 and 2. If it would be case 2 where operators are different, and now you could consider some derivatives here, and now you can have odd spin. And you would get L factorial square root of 2L factorial times, well, in this normalization there is some phase here. I will write it I to the L, I being square root of minus 1. When you divide by some norms, they have, this I to the L, you can ignore it. It is just because when you define a derivative, strictly speaking, you should not use derivatives. You should use I times derivative, which is the momentum. So, well, for odd spin, there is some annoying I here, but I wouldn't worry too much about this I. This is just some phase. Probably if I normalize a bit different my derivatives, I can get rid of this I's, but yesterday night they were there. Okay. So this is what, this is the first part that I wanted to do. And now in the second half of what we are going to do, we are going to understand how do these results talk to the conformal bootstrap. How do we understand all this that we just understood from this modern point of view of the conformal bootstrap and so on. And how can we understand, how can we rederive these results without doing any of these fancy sums and so on, but in a, well, an even more complicated way, actually. Okay. Any question here? But now it's important, I mean, this must be totally clear, because now what we are going to do is explore the conformal bootstrap, which is something a bit fancier. Well, I'd like to know if there is any question here. Yes? No. Okay, there is some confusion there. By this 1 and 2, I don't mean phi 1, phi 2. I mean operator 1, operator 2, and the third operator has some spin L. This is just some notation to indicate a 3-point function between 3 operators. Scalar, scalar, spin L. No, the operators in this picture. Okay, so let me be more explicit. So this case, say this picture here, it's these operators here. So I have 3 operators in this picture. One operator is the operator of type 2 with some spin L. When you have phi 1, phi 2, and some derivatives between the two. That's the one written there in the blackboard. The other operator is the operator phi 2 bar phi 3, just a scalar operator without any derivatives, this one here. And the other operator is another scalar operator without any derivatives, phi 1 bar, phi 3 bar.
Here I'm confused because, for example, these two operators, they are not expressed in terms of O1 and O2.
This is my definition of operator O1. This is my definition of my operator O2. And this third operator is my definition of my operator with some delta and L of type 2. Just to make contact with the notation that we had before, where we have 2 operators, O1 and O2, and they can produce anything non-trivial. The non-trivial stuff is the operator with spin, and the trivial operators are just the scalar operators. I mean, it's just notation. If you want me to call it O ban and O Alice, I can. Ban and Alice. And then I would use here Alice, ban, and spin L operator. I mean, I can, if you prefer. Alice and ban is better. Okay. Very good. So now we want to try to analyze whether these kind of cartoons where we say that from the 4-point function we can read off these results, whether it can work or not. Do we make contact with it? So if this stuff is correct, those 3-point functions that we just computed should appear in our 4-point function. Those quantities in the box there should be what appears precisely here if you consider a well-chosen correlation function where in the middle you will get a sum over all these spin operators that we just described. Okay? Let me make one further comment, is that these theories, you see, they are free theories, and yet there is some interaction between 3 operators. Right? And this is kind of because even a theory, if it is free, if you consider correlation function of composite operators, because of the composite nature of your operators, they will still effectively generate some interaction. And for example, much of the recent developments in trying to understand ADS-CFT and emergence of gauge gravity dualities is in trying to understand the dual of these simplest possible theories. Theories where you have free scalars very much like the ones I wrote here. And you start with the most trivial CFT, just the ones we are dealing with. I mean, it's really trivial as you see, right? Just free scalars. And you start computing correlation function between these composite operators. And then you ask, is there a picture where these composite operators, I can think of them as some sources that I put at 3 points in the boundary of my crystal ball, and then I send some signals in, they interact in the bulk, and this final result of this interaction reproduces these results here that we just computed. And indeed, it exists. It's not a traditional string theory. It is not a string theory like the one that appears in n equals 4. It's called a higher spin theory. It's a complicated theory in the bulk where you have excitations of all possible spins. In other words, you can think of it as a string theory with very, very low tension. It's a theory with many, many massless modes. And indeed, people managed to find holographic duals of theories as simple as these ones that describe this correlation function of free scalars. And perhaps one way of thinking why these theories should be kind of trivial, imagine you have a big composite operator of many scalars here, many scalars here, many scalars here. And then you just draw some propagators between here, some propagators here, and some propagators here. Does it look like a string? Yes, it does. It does look like a string. There is some operators here, and then they get split like some pens. However, these lines, they are just free. So these lines, they can move. There is nothing attaching them. There is no interaction between these lines, and it's like having a string that has no tension. So this is kind of a cartoonish picture of why you could expect that these kind of free theories, where there is no tension holding together these scalar lines, could be dual to a theory when inside your string has no tension, which means that it has no hierarchy of modes, and which will basically be given by a very non-local bulk theory with an infinite hierarchy of higher spin fields. This is what happens. Okay. So having said all these fancy words, let's go back to computing correlation function of free scalars. And let's consider two particular correlation functions. Let me draw two 4-point functions. So these pictures, I mean, if possible, I always prefer to use pictures because, I mean, they are much faster and they also transmit the physics. But if some picture is not clear and you want me to write it in an equation, just let me know. Yes?
Suppose I didn't know that for building a scalar with the higher spin operator, I need a lot of scalars, the sum of a lot of scalars. Would that be some intuitive way to know that the interaction strength is growing with that?
Sorry, could you repeat? That the interaction length is growing with the spin? By the way, is it? I'm not sure. Who is faster, L factorial or 2L factorial? I'm not sure. There is a square root, and it's probably trivial. It's probably 2L factorial is 2L to the 2L, right? And then you take square root, so it becomes 2L to the L. So 2L to the L and L to the L, it's still 1 over 2 to the L, so it decays.
So, well, okay, so that makes the question. I mean, the strength one is kind of more. Is there some physical feature within the dual which would say like high spin operators coupled strongly or weakly?
Yeah. Indeed, many people have been trying to explore the idea. Can it be that you can use large spin operators and expansion of your theory and around the large spin sector as an expansion parameter? Can it be that in general conformal field theories, the large spin is somehow simple and universal, and the bootstrap equations can be tamed, and can we somehow devise some kind of alternative to usual perturbation expansions where we do a perturbation expansion around the physics of large spin? This is what people like Sasha Shiboyedov, Zohar Komagorsky, and so on are trying to develop. And indeed, there's a lot of universality, both on 3-point functions and on the anomalous dimension of operators at large spin, that seem to indicate that such program can indeed be successful, maybe. So there's beautiful things to be said there, yeah. But I don't know much about it. Okay, so now let's consider a correlation function. And I want to consider two cases. And of course, I mean, I introduced this notation 1 and 2 for some reason. It is that one case we will be able to think in terms of type 1 and the other case of type 2. And this is where you will see that I need my 4 scalars. And now I will just tell you what scalars I'm putting here in these local operators. Now, all external operators will be scalars. No one will have spin. It's just the most trivial thing. All external operators is phi square, phi square, phi square, phi square. Everyone just phi square. But with different phi's. So here I will choose phi 1, phi 2. Here I choose phi 2 bar, phi 1. Here I choose 1 bar, 3. Here I choose 3 bar, 1 bar. So you see that once I fix what I choose in one line, the other end, it's not up to me. It is the only possible thing. So if I have a scalar phi 2, it must be phi 2 bar here. So I have this correlation function here. And now for type 2, I want to do 2, and then 2 bar, 3, and then 3 bar, 4, I see 4, the new one, and then 4 bar, 1 bar, and then 1. Okay? This is what I want to do, and it will become a bit clear soon why. Now, why? Well, let's answer why right away. Because what is happening in this case of type 1? What is our intuition? If I'm a diagram served for anything, what can we learn from this? What is happening when you are cutting? What is flowing from side A to side B? Just by charge, you have 2 units of charge of type 1 going from left to right. These 2 lines of type 1 are going from left to right. What is happening here when you cut? Again, just by conservation of charge, 1 line of type 1 is going and 1 line of another kind of scalar is going. So what you expect is that by decomposing this object and this object in the conformal blocks, here we should have access to the conformal block, to the structure constants of type 1, and here we should somehow have access to the structure constants of type 2. We computed both, type 1 and type 2. Right? Is this clear? So now let's see how this goes. Let's compute this in perturbation theory. Let's start with type 1. Okay? Now let's redraw this diagram in an even simpler way, where I just draw the propagators, and I label these points. 1, 2, 3, and 4. Actually, apparently, Okay, this is good. Now, is this the only contribution that I have? So this is point x1, x2, x4, x3. Is this the only Feynman diagram? Do you understand this diagram, right? This is just 4 propagators. This is a field phi square, phi square, phi square, phi square, and I have just the propagators here. Is this the only Feynman diagram? Sorry? No, at 3 level. Just without any interactions. So I just united this line, then this line, then this line, then this line, right? I just rewrote this picture. Is this the only diagram that can contribute, or can you see something else? While you tell me, I will write type 2. Type 2, I have again the same graph. Very good. You can connect them in different way. This line 1 must go to 1 bar, or this line 1 can go to 1 bar down here, right? There is no reason to connect them like a square. So here there is another contribution where I connect these lines like this, right? But I just redo the propagators like this. And this here, it's the only one, because now I'm using the 4 scalars. So 1 must go to 1, 4 to 4, 3 to 3, 2 to 2. There's no other option. So this is the difference between the 2 cases. So let's work this out. This is really a pleasure to do. So what is this? 1 over propagator. x12 square, x24 square, x43 square, x31 square. Just 4 propagators. Plus, what about this one here? 1 over x12 square, x34 square. These 2 propagators are still there, but then these ones are different. x23 square, x14 square. Do you agree that this is what the result gives of this 4-point function? Yeah? It's good? And now let's go on. And let's write it in a proper way. What's the proper way? We should factor this stuff out. What is this stuff for this particular case? Can someone tell me? What should I factor out? What should I factor out? What is delta? So what is the dimension of my operators? Who said 1? Why? So 1 would be the dimension of the composite operator, right? The fundamental field. 1 would be the dimension of 1 scalar, but these are 2 scalars. So 2. So what we should factor out is this to a power 2. And now let's see what we have to fix here. Now in one case we have, so we remove too much, so we still have to put here x12 square, x34 square, now to compensate because we removed too much. And here we got x13 square, x24 square, plus, and the other term, x12 square, x34 square over x23 square, x14 square. You agree? And perfectly, as we expect, we get something times a function of cross ratios. Exactly as we should get just by conformal symmetry. What is this function of cross ratios? This is nothing but u. If you look at u, this is the definition of u. And what about this? Sorry? U divided by v. That is u, which is nothing but z bar, times 1 plus 1 over v, which is 1 over 1 minus z, 1 minus z bar. And this is our 4-point function, or the juicy part of the 4-point function. Who cares about the prefactor? For type 1. This is the object we are studying. What about our effective function for type 2? What would it be for type 2? Sorry? Just z bar, just the first term, just this graph, which is just this, which is just u, so it is just z bar. So now we want to do the following thing. We want to take these functions, z bar and z bar times that, and we want to write them in a nice form. What is a nice form? Is write z bar as a sum of infinite sum of hypergeometric functions. Of course, it's not perhaps the thing, it doesn't look like the most sane thing that you would immediately want to do, but this is what we are instructed to do. If we want to read off what is flowing and to see this picture of what is flowing, this is exactly what we should do. We should now write these trivial, simple, beautiful functions. We should destroy them completely and write them in terms of sums of these hypergeometrics to read off what is flowing between group 1 and group 2. Okay? So let's do it. But before doing it, let's try to see, to think a little bit and to try to have a look at how these conformal blocks look like. Because the picture, the idea is that if you look at this picture, at least if the Feynman diagram intuition is kind of good. Yeah, because if you look at a 4-point function and you want to read off the structure constants from it and the spectrum from it, what should you do? You should take your 4-point function, write it in this way, and the coefficients of each hypergeometric are directly related to the structure constants. Now, this was the basic idea. If you have a 4-point function, I'm telling you that from a 4-point function, by analyzing what is flowing from group 1 to group 2, from group A to group B, you can learn about what is flowing, and you can measure all the energies and all the interactions between these particles. This was the essence of this, of all this, was that if we want to read off the conformal data, what we can do is take a 4-point function and read off its building blocks. Read off its conformal data. We will find multiplication of the C's. We'll find C squared in this case because it's symmetric, so we will find multiplication of the C's, yes. So we will find square of what we obtained before. These square roots will disappear. That's a little bit better, yeah. But otherwise, we will recover what we did before. Yeah? Can I go on? Are you happy? So now, no, that's a very good point. We don't. In principle, what this structure constant gives you is a product of two structure constants. It gives you the probability of fusing two particles into one times the probability of that particle fusing back into two. So if you really want to use 4-point functions to make sure that you get all possible 3-point functions and not just products of, what you can do is consider various different external operators that probe you different products of 3-point functions, and by playing with different combinations, you can then extract the individual ones. But from the most straightforward correlation function, you extract only the structure constant square, or the product of two structure constants. But that's often enough, because if the theory is symmetric, if you consider something symmetric, you see, whatever you produce here you have one 3-point function times another 3-point function, but they are the same. It is just, okay, relabeling 4 by 2, it's the same thing. So you will get just 3-point function squared. So if you get it, you just take square root. Now, what I was saying is that if we look at these Feynman diagrams, by the way, I started considerably later, right? So we are not close to the end yet, right? We have what, 1 hour more? No, seriously, half an hour? 20 minutes? You have a seminar at 6? Ah. But, Okay, then you can watch at Pirso later. I cannot, yeah, I don't want to stop and not go to, I need to finish this example. Otherwise, I cannot do this too the other way. Anyway, when did we start seriously now? We started at 45, so we started 15 minutes later. So we started at 45, was it really 45? So I only have 5 more minutes. Yeah, let's stretch it. Okay, let's stretch it a little bit. Do you have energy? Is it still okay? I mean, it's like stopping a movie when the killer is going up the stairs. I mean, we're not going to turn off the TV now. Now we have these objects we want to explain and see if we do get this box or not. Very good. So what I was saying is that if our intuition serves us right, you see that it looks like what you want to do is sum over operators of twist 2. That is, operators that have 2 scalars and then a bunch of derivatives eventually hitting these scalars. Right? This is what it looks just from this diagram. So it looks like perhaps the most important, and who knows, maybe the only one, and we will see that it will be the only one, but definitely one that we have to consider, is the conformal block for the exchange of operators whose dimension is the spin plus 2. Okay? So let's consider this conformal block as function of z and z bar. And this is what? It's z bar over z minus z bar. It's this factor that is written there. And then we have h of what? Put delta there to be L plus 2. So you get here L plus 1 of z. And then what is nice is that h for twist 2, the second one is trivial. Because if delta is L plus 2, here you get h0 of z bar. And this is just 1. It's just hypergeometric with 0 entry, so it is just 1. Minus the same thing with z and z bar exchanged. Okay? So if something can be written purely in terms of twist 2, what would be the signal that this is the case? The signal would be that up to some simple factor of z and z bar, the rest is a function of z minus a function of z bar. Right? If it is not, if it's more complicated, it cannot be expressed in these functions. You agree? I cannot write a linear combination of such functions. By definition, I will get this factor times function of z minus function of z bar. You agree? So let's check. And indeed, let's look at the second example. F2, which is equal to z bar. I can indeed write this. I can write this as z bar over z minus z bar times function 1 of z minus function 1 of z bar. What is this function? Z. So our exercise is take z and express it as an infinite sum of hypergeometric functions. So it becomes even more ridiculous. It's looking more and more ridiculous by the time. But this is what we are instructed to do, what we simplified our problem. Now it's not function of 2 variables, it's really you have z, and you want to write z as an infinite sum of hypergeometric functions. Okay, we are going to do it soon. But let me tell you that, and so this means that our intuition was correct. That indeed, if we cut, it will be enough to sum over twist 2 particles. But if our intuition is correct, you look at this diagram and you think, come on, where did I get wrong? If I cut, it should be also the case. But it's not obvious. If you look at this function, it doesn't look to be the case now that it is. But it is indeed. You can check. I'll let you check that F1 is equal to z bar over z minus z bar. And indeed, you can also write it as F2 of z minus F2 of z bar, where F2 of z is equal to 1 over 1 minus z. Okay. It's a bit non-trivial. You have to check. Just plug. You make slash factor. And you make slash factor in the previous expression, and you get the same. So that this is a representation. Okay? So what do we conclude? We conclude something nice. We conclude that So then the claim is the following, is that in these theories, both in type 1 and in type 2, both in type 1 and in type 2, we are led to the last thing that we have to show. We have to write f, a of z. A can be 1 or 2. Right? And we simplified our problem to say that we should write this f as a sum over all spins, L from 0 to infinity, structure constant of type A between scalar, and spin L, square, because of what you said. He disappeared already? Oh, no, you're here. Okay. You're with your hand covered. Because of what you said, you get C squared, times this hypergeometric there, Z, to the L plus 1 times hypergeometric F to 1, L plus 1, L plus 1 to L plus 2, comma Z. Okay? So now it's a totally well-defined exercise. What we should do is take this function, f of z, fa of z. It can be z in one case, or it can be this slightly more complicated function in the other case, and write it down as a sum of hypergeometrics. So let me just finish this exercise. How do we do this? What is an hypergeometric function? An hypergeometric function. Now how do we solve this problem? We just Taylor expand both sides and compare powers. Right? So what is this f? This f is a sum of k equals 0 up to infinity. Pocamer L plus 1k square. Pocamer 2L plus 2k, k factorial, z to the k, where Pocamer, a, n, is defined as gamma of a plus n over gamma of a. You agree? It's just definition of an hypergeometric function. It's just a sum of a bunch of gamma functions. Do you agree? So let me tell you what the final problem is. So you see that what happens is that at spin L, the result starts at order z to the L plus 1. Because you have explicitly z to the L plus 1 times something that starts with z to the 0. So the first terms in this expansion, you only care about the first terms in this sum. So from the leading term here, right? So the idea is that from the leading term at small z gives you directly, let's call this object PL, gives you directly P0. And then the subleading term, once you know P0, gives you P1, and so on. You agree? So if you know the leading term, you read off the term that goes like z. It's only L equals 0. Then once you know go to z square, now you go to L equal 1 to get z squared here, and also the term of z squared coming from L equals 0. It's a triangular problem, and you just solve it, More precisely, what we have to solve, let's write just very explicitly using the form of hypergeometric, so that there is nothing to hide. What we have when we compare coefficients is what we derived is the following. If we collect coefficients, we have that there is a vector, Vn, from the left-hand side, that is the coefficient of z to the n, or maybe z to the n plus 1, I don't remember, which would be defined as collecting the power of z. So you would get a sum from L equals 0 up to n minus 1. L plus 1, choose k. I'm a bit tired, I confess. K is n minus L minus 1 square, 2L plus 2, n minus L minus 1, n minus L minus 1 factorial. Times our key object. This is really what we are after. Let's put it really in some nice color. Times our object PL. This is the object we want to study. On the one hand, it's what we get by collecting power of z in the right-hand side. And what we want to solve is the problem that this vector is equal to a problem Vn on the right-hand side that depends on A, or whether it is type 1 and type 2. And what is this vector? For example, if you are at type 2, what is the Taylor expansion of Z? It is just Z. So it is just the vector that is the infinite vector where the first entry is 1 and the other ones are 0. What about for operators of type 1? Let's see. For operators of type 1, this is just Z plus Z squared plus Z cubed plus Z4 plus Z5 plus Z6. You can see the pattern. And you add Z to this. So the first one is 2. And everyone else is 1, 1, 1. And now you see what you do. Let me be more explicit. You impose V1 left-hand side equal V1 right-hand side. And this fixes P0. Then you impose V2 equal V2. And once you know P0, the next term with n equals 2 contains P0 and P1. So you fix P1, etc. And then you do this. You put in Mathematica. My plan would be to have coded a little bit of Mathematica for you, but we don't have time, I think. So let's just write what the results are. And then this is what you get if you start doing this table. You start generating this table. And this is what you get for PL. You start getting numbers like this. 2, 0, 1/3, 0, 1 over 35, 0, 1 over 462, 0, 1 over 4,655, 0, tac, tac, tac. And this is what you get for type 1. And for type 2, you start getting 1 minus 1/2, 1/6, minus 9 over 80, 1 over 70, da, 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 for type 2. Okay? And now let's go here. And the claim is that this is exactly what matches these numbers here. So let's see that it works. So first of all, look that when L is even, the square of this and the square of this differ by a factor of 2 when L is even. And indeed, you see, here you have 1, here you have 2. Here you have 1 over 6, here you have 1 over 3. Here you have 1 over 70, 1 over 35, and so on. So it's good. And then, furthermore, note what we have here. We have 1, 1/2, 1/6, and so on. And you can really check that these numbers are nothing but the square of these factorials here. And this was actually how people first derived these structure constants. It was actually by doing this crazy exercise of writing Z as a sum of hypergeometrics. So this is, if you want, what I wanted to tell you today. There's, even here, I think this doesn't exhaust everything we could do. I think there would be something fun that would be interesting to do, which would be to try to analyze this OPE from this channel. When these operators, you study what flows from these operators to these operators. It's from this U channel. It should give the same thing. It should be also possible to do. But if you analyze the OPE, I leave it as a homework. If you want to analyze what happens when you decompose the result, thinking of this as being operator 1 and this as being at operator x2, now you see that what flows from this to the other 2 points are 4 scalars. So it looks more like a twist 4 contribution where we have 4 scalars. It should be different. The analysis should be different. The structure constant should be different. It should not be no longer twist 2. I think it would be interesting to play a little bit, and I leave it as an exercise, homework, to play with U channel and basically repeat all these shenanigans that we have been doing, but now thinking of the expansion from this other channel point of view and understanding how this connects with structure constants and so on. This field of computing 3-point functions and computing 4-point functions and weakly coupled conformal field theories and understanding the interplay between the two and so on is something that is not very well developed yet. I mean, conformal blocks were found very recently. There are not that many theories where we can compute many things at very high loop orders that we can use as a laboratory for checking ideas. And one idea where people have been pushing these ideas is in n equals 4 super Young Mills. N equals 4 super Young Mills is a theory that has scalars. It has many complex scalars like the examples I did. And you can think that this is kind of a warm-up for studying that theory if you want. You could imagine starting with some correlation function of some scalars, but then in n equals 4 you start adding interactions and so on. But there is a beautiful field which is basically wide open of understanding structure constants, correlation function, the OPE, and how things talk to each other, and how can we try to understand these correlation functions at any value of the coupling. That I think is something very interesting and that people are now starting to explore. Many of us here at PI, for example. Okay. We are good. We managed to finish the movie. So it works. Any question? Is it clear? Should I summarize or I summarize tomorrow? I mean, is it clear what we did? So we have 4-point function. We analyze it in the OPE. We see that we do get beautifully the 3-point functions we computed before. We get functions of cross ratios. We understood explicitly how to do the sum over conformal blocks and how to extract these coefficients. I do encourage you to play a little bit with this. Try to read it again. Implement yourself. Find these numbers in Mathematica, for example. Just solve these equations and check that you do get these numbers and so on. Check that the sum that we wrote there does give this 2L factorial. Try to understand with. Play a little bit with this. Play yourself. Play with this. All these identities and everything we saw, because it's kind of important to get used to. I mean, once you get used to these conformal blocks are nothing, as I said, like a Bessel function or like a spherical harmonic. But the first time you see it, often people get a bit confused in distinguishing dynamics from kinematics, and it is indeed important to play a little bit to really absorb this subject properly. Okay, see you tomorrow.